We spoke a little bit before about how something can expand. For example, a wire, a telephone wire, or a train track, heat, and so on. Basically, we're talking about solids and how they expand. When we're talking about gases, we're going to be using formulas like this. Or when we're talking about solids, we want to come up with some formula. Obviously, it's more simple. We don't need to talk about the atoms banging around in a solid. There seems to be a relatively simple way that solids expand. What would you say could be a formula that will tell us okay, what we're looking at, let's say, is the amount of expansion. L is the length of an object, and we want to know how much the length changed. The length of a telephone wire, the length of your foot, the length of a steel rail. What should that depend on? Change in the length. Okay, you're heating something up, it's getting hotter, and you notice it expanding. So what should that change in the length depend on?
The change in temperature.
Change in temperature. Okay. There's one other, not exactly subtle, but let's say you have a string that's a mile long and a string that's a meter long. Okay? And they're in the same room. The room has risen in temperature by 10 degrees or something like that. Will they change by the same length? No. So what else has to be in here? Fundamentally, are they different? Let's say the 1 meter length and the mile long length. Are different things happening in there? No, just the one is longer. So what we really want is the proportional change. Okay? The amount of change per meter, let's say. The amount of change per centimeter. And then it'll be the same thing for, doesn't matter how long the thing is, the amount per centimeter per meter is the same. So really what we want to do is relate this to the change in temperature. And we'll just need some kind of constant of proportionality here for the units and so on. Not only for the units, but would you say that your foot and a metal rail and a string and all that kind of thing, all those should just have this form? They may have this form, but they're different materials. Different materials might react differently to different temperature changes. So we're going to have something here which is going to depend on what object it is, what it's made of. All the different coefficients of linear expansion alpha for different materials. And when we're doing science, where we're looking at the natural world, we're looking at phenomena, we want to find patterns of regularity, things that repeat themselves, that we can come up with some kind of cause and effect. Applying our intuition about the things that we observe, and what we end up trying to do is find regularities and patterns in nature, and then try to give it some kind of quantitative description, come up with a mathematical description of it. Right? Now there's kind of two different ways to do this. One, we can start with experiment. Two, we can start with theory, with equations. One is you can just start doing all kinds of phenomena, throwing things around, looking at things, and just try to see if there's regularities and try to figure out what the regularity is. Or you can do a little bit of that and then go and sit and think and try to come up with some kind of an equation and then test your equation. But usually the two go partly hand in hand. You couldn't come up with an equation without having some familiarity with the kind of processes or phenomena that you're dealing with. All right, we came up with this equation. All right, we felt that this was, logically speaking, based on our experience, the simplest possible formula that we could devise that would take into account what obviously has to be taken into account and nothing else. Right, we had the fractional length change is simply proportional to the change in the temperature with some proportionality that we recognize to be different for different materials. Then we have to go into the lab and test it and see if it works. All right, obviously we've never been able to come up with this formula without having the experience that things expand when they're hot, or contract when they're cold, or as with water, as we discussed, in certain points, the opposite. So we would never think of this without having familiarity with the phenomena. We also wouldn't know that the variable that's important is the temperature, and so on. We wouldn't necessarily know that different materials expand with different amounts, different proportionalities. But once we have a little bit of familiarity with that, we can come up with this. Now, even that part is not something that's automatic. Obviously, most people would not have even thought of the fact that things expand when they get hot as a phenomenon. They may have noticed on certain days, for some reason, their shoes didn't fit well, and they kind of ignored it and said, I don't know, something happened. The way I slept, maybe my foot swelled, or something like that, right? They may have noticed here and there, maybe ice expands, but they didn't think of it as ice expands. That if you ask them, they would say, yeah, you know, you're right. The ice cube tray kind of overflows more than the water amount that I put in. But it takes a certain kind of mind to look at all these different disparate phenomena, put it together, and say, things expand when they're heated. Again, as opposed to water, right? And in fact, if you notice the water example, which is very prevalent, it might throw you off, and you might never notice this phenomena, because you say, well, something gets bigger, something gets smaller, maybe you think there's no pattern. But if you study it carefully, you'll see that there is a pattern. You'll tie together all these different phenomena, and you'll come up with this rule. Things change their length when they undergo a change in temperature. And usually, it's proportional to the temperature. That the more temperature increase, the more the change in length. And then you'll notice, let's say, an exception with water. And then, using that, you'll come up with something like this, and then you can test it. Let's look at, for example, we have this river outside over here. It's going to be getting colder. It's going to be winter soon, or maybe it's already considered winter. And temperature is dropping. Okay, we're looking at the river. The temperature is dropping. The surface of the water is getting colder. All right, and then it's going to be in contact with the level of water right beneath it. So whatever heat there is in the water beneath it will be sucked into the layer on top of it, and that's going to be then sucked into the air. So like heat is being sucked out of the river into the air. The air is cold, right? And it's kind of sucking heat out of the river. So the upper layer of water, which is in contact with the cold air, is going to get cold first, before the next layer does. As it gets cold, when something gets cold, what happens to it? It contracts, right? Now here we're talking about a volume contraction rather than a length contraction, but basically it's the same thing. If a length contracts, then in all distances, also in a liquid, it'll contract. And so what we're going to have is delta V over V is some proportional constant times the temperature. Or the proportional constant might be different for different materials. Okay, the proportional volume change will be related to the temperature. So the water contracts a little bit more. What's going to happen if the water becomes a little more dense? What's going to happen to the water that's more dense on the top? If you have dense water over here, what's going to happen to it? Right.
Well, there's freeze, but they won't.
Well, before it freezes, let's say it's just getting colder. Okay, so it's more dense now because it's contracted. So what happens to it? It'll sink, right? If you take a dense material, if I put this in water, what will happen? It'll sink. Why? Because it's denser in the water. Right? Okay. So the denser water goes down to the bottom. Not in as simple a way as this. Obviously, it's not a block, it's not a piece. But basically, the denser droplets or water molecules that are slower, or whatever you want to call it, are going to gradually find their way more towards the bottom, leaving warmer water on top. What's going to happen to that warmer water? Same thing will happen. It'll go to the bottom. Okay? Again and again and again. Over a period of a day or several days, what's going to happen is you're going to have cold water at the bottom, the coldest water at the bottom, a little cooler, a little warmer, up to the warmer water will be on the top. Slowly, the temperature of the air drops. It's getting closer and closer to freezing. You can have very cold water, like close to freezing water at the bottom, going up to the top, and the water at the top is getting frozen also, getting close to frozen. What happens when it gets to freezing point? It starts turning into ice. Right? Ice is denser, it falls to the bottom. At the top, you have liquid. More ice forming because of the cold air. What happens? You have ice building up from the bottom of the river. Right? Ice building up. By the middle of the winter, the whole river is frozen. all the way down to the bottom. What happens to the fish?
They die.
They all die. In the spring, the river thaws. What about the ocean? The ocean is deeper, it takes longer, right? But you have places in the north where the winter is 6 months or 7 months, really frozen wet. Right? So you may have enough time for the whole ocean to freeze. What happens to all the fish? They die. What happens to all the plankton? Well, maybe it can survive in frozen, I don't know. Spring comes, thaws. What happens? No fish. They're all dead. Nobody laid eggs. Maybe there were some eggs that may have survived. I don't know, frozen eggs probably doesn't. You have to freeze it in a certain way, maybe for like frozen embryos and so on. All right, so then we have a question. Does this really happen in the world? No. Right? In fact, just from your own experience, what does happen?
The top freezes first.
The top freezes and not the bottom, right? Animals, sometimes fish, you chop a hole in the ice, and fish, submarines go under the ice pack and so on. So why is that?
Currents under the water. I mean,
Okay.
because the water moves, so
There are water currents and water moving, so maybe it doesn't happen quite like that. But let's say, look at the water out here. How fast is it moving? I don't know if you can tell exactly. There may be currents underneath. It doesn't look, at least, it's not like a rushing river. Okay, but there may be currents underneath. I don't know. But let's take the assumption that there aren't really currents, even though it's a river, not heavy currents. It doesn't seem like enough to prevent that from happening. Of course, in this climate, it may not ever get so freezing cold, lasting for so long that the whole river would freeze. But certainly a little bit further north in Canada and so on. So, what happens? The answer is that although basically just about everything else contracts when it gets colder and expands when it gets hotter, water doesn't. Water does the reverse at some point. And because of that, instead of the ice sinking down to the bottom, the ice stays on the top. So again, you have water, warmer temperature, it's whatever, just circulating around. Air is getting colder, the top layer gets colder and colder, it starts going to the bottom. At some point, when it gets to 4 degrees centigrade, it stops contracting when it gets colder and starts expanding. So what happens instead is the colder water stays on top. Now what happens when you put ice in an ice cube, in an ice tray, water in an ice tray and you freeze it? You open up, what happens? Does it have more volume or less volume?
more.
You always notice that it has more volume. You put it in a bottle, the bottle, if it's a plastic bottle, it'll expand. If it's not plastic, it'll smash. If it's glass, right?
But
Ice expands. The colder it gets, at least to some point, right, it'll expand more.
doesn't
So
have,
water behaves exactly in the opposite way from just about every other material.
doesn't it have anything to do with the water has gases and oxygen?
No, it does have other things in it, but the other gases or whatever other materials will contract the colder they get, but the water itself doesn't. All right? So it's only because water has this strange anomalous property that it does the reverse of what everything else does, that the oceans and the rivers don't freeze and that the fish don't die. Now, obviously, if all the fish died and the vegetation died, it would be very bad for everybody else. Okay? So the whole life cycle on the planet really comes about or is enabled by the fact that water has this strange anomalous property. Why does water have this strange anomalous property? It has to do with chemical factors in the water, which have to do with properties of the atomic interactions and the fine structure constants and so on. It goes down like more fundamental levels, and you can study why it is that water behaves in this particular peculiar way. It has something to do with fundamental laws of nature. Okay, the constants are a certain amount, and because they're a certain amount, then it happens this way. It had been a little bit different. It wouldn't have been. Basically, therefore, life as we know it exists because, at least to some degree, water has this strange property. And there may be life forms that don't exist with water or need water, of course, and then that would be a condition for their arising. But basically, when NASA, let's say, is searching for extraterrestrial life, they're assuming pretty much that life will be where there is water. All right? Life evolves maybe in the water, possibly. Life, living organisms are composed to a large degree of water, and they need water to stay alive. All right? So water figures very prominently. If the temperature varies a lot, so that it goes down to freezing, which is pretty likely on most planets if they're rotating, or if they have an axial tilt, then they'll have seasons, they'll have winters and so on. Or depending how far away they are from the sun or from whatever star they're revolving around, it's likely that water will encounter conditions where it freezes. And if life is dependent on water, then it's possibly the case that this anomalous behavior of water contributes to the possibility of life in other places. Okay. I'm going to go a little bit more over this thing about moles, and again, it's something you probably learned in chemistry, but I'll go over it a little bit. Section 39, you have problem solving with the ideal gas law. It's all plug-in examples, all right? If you have P is equal to nRT over V, and this is has to do with the amount of molecules, all right? For example, how much is nR equal to? According to this equation, PV over T. All right, so if you have some process where the number of molecules stays the same before and after the process, what else stays the same before and after the process? PV over T. Right, if this is some number, and this number stays the same before and after, then PV over T before is equal to PV over T after. So if you're given this before and 2 of the 3 after, you can figure out the third one. Now, this equipment that we have to test it is a little bit elaborate. We have 2 things that have to be plugged in. All right? Now, in theory, do we need to plug in anything to test this? What would be the simplest apparatus to test this equation? How would you test this? Let's say you had no equipment in particular. Could you test it? Or is it impossible to test otherwise without, let's say, this kind of equipment?
Well, you could test something just with the temperatures that we have, you know, if it's cold outside and hot inside.
Okay, so you have a ruler and you have different things. You can use your feet, you can use a metal something or other, right? You can look at telephone lines, as we spoke about, right? And you take some kind of qualitative measurement, like we did with the door, the lab that we did with torque, putting a book on our arm at different places or pushing the door at different places. That was an experiment, but it was qualitative in the sense we didn't have a number, but we can certainly see a pattern. The further away, the harder, and so on and so forth. Okay, the same thing we can do, we can see, the more temperature increase, you write down over the period of the year, during the winter, during the summer, every day what the temperature was, and what the length of these different materials were, and you come up with something. Now, let's say you want to do it on one particular day, not over a period of the year, and you want to change the temperature. So maybe you can use your refrigerator and your freezer and your room temperature. Plus, you can also generate heat like this. Okay, the refrigerator, of course, is an electrical device. But let's say without electrical devices, you can take a piece of metal, a thin piece of metal, rub it in your hands like this till you generate enough heat. You don't know what the temperature is, but you know that it's a certain rise in temperature, and see if it's expanded. Now, you might find that the expansion is so small that it's not noticeable. So then you'll need to take different kinds of metal, or a certain kind of precision instrument that lets you measure the length change. Now, what's one way of measuring the length change that'll give you more precision? It would be taking a longer object, okay? Because a fractional change will be more noticeable. All right, if it's a 1 1 centimeter object and it changes by 1%, you might not notice it. But a 1 meter object changed by 1% is 1 centimeter, you might notice it. Heating up a 1 meter object might be harder than heating up a 1 centimeter object. All right, but in theory, it's possible to do. We would still need a thermometer if we want to get exact changes. We'll still need a ruler if we want to get exact changes, right? We might need a certain kind of environment, like some kind of insulation, like a cork, to keep something at a steady temperature. But we don't necessarily need all this elaborate equipment. The reason I'm saying it is just not to get confused with the equipment that we did at experiment. We had to plug in 2 things, we had a lot of wires, we had readings and things like that. Basically, what we're doing is taking a piece of metal, warming it up, and measuring how much the length increased. Okay? But in order to get an insulated bars, we have the torque in order to get it hot, we have the steam in order for it to be safe, we have all these tubes and pipes and things where there's no steam exposed in order to know that it's really touching. So we have this electrical thing, but we don't really need all that stuff just to do an experiment, especially if it's qualitative. Okay, now what's the important aspect of doing this experiment? Obviously, again, the purpose of the experiment is not to verify that the people who wrote down the coefficients of expansion in the book are correct or did it correctly. We're assuming that it can be done correctly and they took the pains to do it and they did it correctly. What are we trying to figure out? Partly just experience seeing it with your own eyes and it expands, but even that is not so important because everybody has seen expansion under or contraction due to temperature change. What we're doing is learning a little bit of the difficulties in actually coming up with a precise measurement. Learning what are the error factors that creep in, how to take that into account. Okay, the real world as opposed to just some kind of abstract theoretical construct where we can neglect air resistance and there's no friction and we neglect the mass of the pulley and so on and so forth. Sometimes when you don't neglect all those little things, it makes such a tremendous complication that you can't actually do what you set out to do. Sometimes you find that there's a phenomena so subtle that if you neglect that little tiny change and you say, well, I don't know where it came from, it doesn't matter, that turns out to be the most important phenomena around. Okay? There are different ways that heat can be transferred from one to the other, from one object to the other. You can have radiation, for example, let's say the sun. The sun shoots out lots of heat, but there's vacuum in between us and the sun. So there's no air, there's no gas, and the only way that energy can get from here to here without anything in between to transmit it is through radiation traveling through empty space. If you have two hot objects that are touching each other, they don't need to radiate in order to warm each other up. You can have heat transfer directly. How does it transfer? We have the molecules vibrating over here, and the molecules up here, and this one bangs into that one, and whichever one is vibrating more causes the other one to vibrate a little bit more. It loses a little bit, and it gains a little bit. And that's what we call transfer of heat. So the temperature of this one is dropping, the average molecular kinetic energy is dropping, and the average kinetic energy of the molecules here are increasing. What will happen? Eventually, the two averages will coincide, and that's what we call that the temperatures become the same. Okay, so whenever you take two objects of different temperatures, they eventually find some temperature in between them, and they remain at that temperature if they're insulated. Okay. Now, another way that heat can be transferred is if hot things actually travel into other cooler things. You can have, let's say we talked about the water, the surface level of the water is heated by the sun, let's say. It becomes, we had the opposite. We had, it's getting cold because the air is cold, it gets more dense and falls down, except between 0 and 4 degrees, right? So there's colder water traveling down, or you can have hot air rising. So you actually have hot things or colder things moving and coming into contact with things of a different temperature. And that's called convection. Okay, and again, this is all in the book. So you can have different ways that heat can be transferred, and there are different equations that describe how the heat is transferred under those circumstances. In conduction, when we're talking about two pieces of, let's say, metal that are separated by a certain distance, all right, you have a hot piece of metal here, a hot piece of metal here, and somehow they're all insulated, and we're just talking about the interaction of these two. What would you say should govern the rate of heat transfer? We're going to use the letter Q for the energy of heat. It's basically kinetic energy of molecules, okay? And it's going to change with time. We're going to have a flow of heat with time. A certain amount of heat energy, in other words, kinetic energy of molecules, whatever, is going to flow from one object to the other in a certain amount of time. All right? And you have, let's say, in the book they have this picture of two metal rods, and they're separated by a certain distance, and one is hotter than the other, and there's heat flowing from one to the other. Okay? What do you think might govern the heat transfer, or the rate of heat transfer? not the total amount of heat, but the amount of heat per second, let's say, that goes from the hotter one to the cooler one. What factors might be involved? What?
The molecules in between them.
Okay, let's say that we have, let's eliminate that either, if it's not radiation, but it definitely does depend on the material between them, okay? But let's
Disregard.
say in air, okay? Let's say, given that it's air, what should the rate be?
Should be
Okay, what other things will it depend on?
Distance.
Yeah.
Okay, the distance between them, certainly, and where should that appear?
This.
The further the distance, the less.
Okay, so it'll be, if this is L, it'll be on the bottom,
Mhm.
okay? What else?
The state of
The difference in the heat.
Right, the difference in the temperatures of the two objects, if we call this T1 and this T2, so let's say delta T or T2 minus T1, right? The greater the difference between them, the more it will transfer. Obviously, if you put something very, very hot and something cold, okay? What else might, okay, this is a little bit more subtle, but the heat is coming out of this edge, so to speak. Okay, so the more area there is here, right, the more
Well,
heat is coming out.
the greater the surface area.
Okay, so it's also proportional to that cross-sectional area of the thing, and here also the more heat it's able to absorb. And it'll depend on what material it is. All right, so you'll have some kind of a constant. All right, and that's the formula that they have in the book, and that's basically what it turns out to be. A very logical formula, again, basically the easiest possible formula that there could be, given the circumstances. Okay. The other way that we spoke about is radiation. In radiation, there's a more complicated formula, and this formula, the more complicated one for radiation, can be found experimentally, and you can also find it theoretically using very complicated physics and mathematics and so on. We're not going to do that, so we're going to write it down, okay, without going into it in depth. There, for radiation, you're going to have a heat transfer going to be proportional to the fourth power of the temperature of that which is losing the heat. Okay. Equation 14. Okay. Also, of course, the cross-sectional area of the object, and you're going to have some proportionality factor. This is equation 14.4. You don't have to write it down. It's going to be a more complicated formula. So we're not going to go into the logic of that formula, why it's t to the fourth. It's something that if you take more advanced physics courses, you'll learn why, and it's actually something very, very interesting. You have the different units, calories. You may know that when you talk about a calorie, it's actually a kilocalorie in the terms that are used in physics, like 1,000 calories. And all these things are just definitions, BTUs and joules and calories and so on. You probably encountered this in some kind of high school chemistry. There's two examples showing you how to convert in terms of energy from calories that you burn by walking, let's say doing a certain amount of work against gravity in your body, and how many calories it burns. Just converting in others different forms of energy. Heat is just a form of energy. Calories is just a measure of that energy. Specific heat, we spoke about this briefly. The metals that we were heating up, or any other matter that we're heating up, if we want to heat it up, we have to add heat to it. How much heat do we have to add in order to change the temperature? Obviously, the amount of heat will be proportional to the change in temperature, to the amount of mass, amount of molecules that you have to raise their temperature, right? In other words, that you have to increase their kinetic energy. And it'll be a little bit different for each material, just as we found today. What is the simplest possible formula? Okay, the amount of heat that you have to add to something to change its temperature by an amount delta T will be obviously the delta T times the amount of stuff there is times some kind of constant that has to do with that material. Q is the amount of heat that you need to transfer from one body to another in order to raise it an amount of temperature change delta T. So how much heat do you have to add? You have to add an amount that's proportional to the amount of temperature change, that's proportional to the amount of material. Obviously, if you have a small piece of metal and you want to raise it 10 degrees, you have to add less heat than if you have the same metal but much more of it. You have to add more heat to change it the same amount of temperature. Okay, so the amount of heat that you have to add proportional to the amount of temperature change, the amount of material, and what material it is. It can't be any simpler than that. Obviously, if you left out any of those things, you would know right away intuitively that it's wrong. Calorimetry, again, I think you may have had calorimetry in high school chemistry or something like that. Very, very, very simple plug-in problems. When you take a metal, and they tell you, let's say you take steel at 20 degrees, and there's 2 kilograms of it, all right? And you put it into water at 10 degrees. So obviously, if the steel is hotter than the water, the steel will lower the temperature to lose heat to the water. What temperature will they get to? Okay, they'll get to some common temperature. You can figure it out by the amount of heat lost by the metal and the amount of heat gained by the water. How much heat is lost by each one? You take the mass, you take the specific, that little constant that tells you what to plug in over here, and the change in the temperature.
Okay, and then the one above that, the change.
The one above it, this is for radiation, only for radiation. Okay, and that's the amount of heat per time that something radiates.